Hello, welcome. In this video we are going to see a special kind of group. This group is called a factor group or the quotient group. Factor group or quotient group. And we have a result that tells us that the set that we are going to define, say the set is will be defined in the statement of the theorem, that is actually a group, and that group is the factor group or the quotient group. See, the statement of the theorem is, let G be a given group, and G be a group, and also H be a normal subgroup of G. So we have a given group and a normal subgroup of the given group. H is the normal subgroup of the given group, and we define a non-empty set. We define G bar H. G bar H is the non-empty set. It is defined as the set AH, such that A is an element of G. We choose an element, arbitrary element A of G, and that element is used to pre-multiply the normal subgroup of G, and using this method we get different elements, and all those elements which are obtained are taken in one set, and we can show that that set acts as a group. So for establishing that it's a group, or for proving that it is a group, actually we want an operation which is defined on that non-empty set. This is the non-empty set, G bar H equal to set AH, given such that A is an element of G. In this non-empty set we want a binary operation, and that operation is given here, AH dot either or AH BH equal to, where A and B are two elements of G, AH dot BH equal to ABH. So this is the way we can combine the two elements in that non-empty set. Next we discuss the proof, steps of the proof. See, in order to show that a non-empty set is a group, first thing we require is a binary operation which is defined on that group, that must be well defined, and then we have to show that there exists identity element. Next point that we want to show is that for any element there exists the inverse, and we also want to show that associativity is satisfied by any three elements taken from that non-empty set. So one by one we are going to show this, but as the first step we want to show that the operation, the binary operation which is defined here, this is that binary operation, it is well defined. For proving that it is well defined, let's take four elements of G, A prime, B prime of G. We take A prime, B prime. Four elements we take because we have equality of, we have to consider equality of a pair of equalities we have to consider of elements, and then we have to combine them using that binary operation, and then finally we want to establish that well defined, to show that it is well defined. So now we suppose that after taking these four elements, we suppose that AH equal to A prime H and BH equal to B prime H. Suppose AH equal to A prime H and BH equal to B prime H. In that situation we want to show that AH dot BH or AH operation BH equal to, if this is the situation, if then that can imply that A H dot BH equal to A prime H dot B prime H. So that is the thing that we are trying to establish now. But you know, in this in the current situation, you know, if this is true, if H equal to A prime H, then we know that A prime is an element of H and vice versa. That is A prime. If this is true, if H equal to A prime H, then we can show that. Earlier we have seen that already. We have seen that. See, in the previous our discussions, we have established that. But you know, if H equal to A prime H, you should remember that can imply that A prime is an element of H and A is an element of A prime H. That also is true. A is an element of this element. A is an element of A prime H, and A prime is an element of AH. So why? Because because A prime is an element of AH. It's because AH equal to BH. Using this, this is the reason for that. AH equal to BH. If and only if, it's because we know that AH equal to BH if and only if A is an element of BH. So we have already established. It's an established fact already. Yeah. So now. You know, A prime, therefore, and due to this reason, in this stated reason, A prime is an element of H. Due to this reason, you can see, you know, you can write that, you can find an element H1 from H, from the set H, such that A prime is equal to AH1. See, therefore, due to this reason, yeah, A prime is equal to, you can write that A prime equal to A into H1. A into H1, and this H1 is an element of the normal subgroup H, and also you know, B prime is equal to B into H2. In a similar way, we can say that B prime here, considering this the second equality which is given here, you can write that B prime is equal to B into H2. See, then H1 and H2 are two elements of H, capital H. Okay, then we write A prime B prime of H equal to, then we take A prime B prime of H, and that actually equal to A prime H dot B prime H. A prime B prime of H is equal to, then replacing A prime by AH1 and B prime by BH2, we can write that it is AH1 BH2 H. And now you can see that there are four elements. All these four elements belong to the same group G. Okay, and now you can apply associativity here in a convenient fashion. You can apply associativity here so as to rearrange the elements in a particular way. Actually, we will do that. See, by rearranging this here, we get, you can write that this is AH1. Okay, now before applying that associativity, you can see that H2H. See, this H2H, because H2 is an element of H. Since H2 is an element of H, this H2H, when it is an element of H, it can be equal to H. When if H2 is an element of H, so H2H will be then H. Thus you can substitute or you can replace H2H by H, a single H, and then we get that AH1 this is BH2 BH AH1 BH equal to by it's equal to AH1 then HB. Why? It's because, see, this portion, this part, and this part can be replaced by BH, can be replaced by HB. Why? Due to the reason, it's due to the reason that H is a normal subgroup. Just because of the reason that H is a normal subgroup. So BH equal to HB for any element B which is taken from G. Okay, and therefore we get that H1 BH equal to AH1 into BH equal to H1 into HB. After that, now and once again applying the fact that h1 is an element of H. Again, by knowing that h1 is an element of H, noting that h1 is an element of H, you can replace this part by H, a single H, and we get that. See here, AH then B, AHB, AH into B. And again, since A is an element of the group G, A is an element of G, and AH is equal to HA. Immediately we get AH equal to HA due to the very reason that H is a normal subgroup, and thus what we can do now here, or HB also, that also can be since AH is equal to that we want to replace HB part. Okay, since HB is equal to BH, here we have this portion can be replaced by the quantity by the value BH. It's because HB, since B belongs to the group G, then HB equal to then BH also in this portion, and that expression is replaced by BH, and finally we get that ABH. So we have started by considering A prime, B prime, A dash, B dash of H, and by doing all these the steps, these simplifications, finally we obtain that AB it's equal to this quantity equal to ABH. This shows that the operation which is defined is a well-defined operation. And therefore multiplication is moreover the multiplication depends on only the cosets and not in the coset representations, and does not depend on the coset representations. Okay, now let's think about the identity element, existence of identity in the set. Let's consider EH. E is the identity element in the group G. Then if you take the identity element into H, that will be equal to H. Since EH equal to H, it can act as the identity element in the current situation. Okay, therefore there exists identity element. Now suppose AH is an arbitrary element of G bar H. Let AH be arbitrarily chosen, be an arbitrarily chosen element from G bar H, and then we can consider, depending on that that element chosen AH, we can take the element A inverse of H. Since A has inverse A inverse, S inverse is A inverse, and using that A inverse can be used to pre-multiply H. That element will also exist there in G bar H. And now let's think about that operating the first element with the second element H, then dot A inverse of H. That will be then combined to A into A inverse of H according to that definition, and then it becomes these two operates and it becomes 0. So EH equal to H. That again be written as A inverse into A into H equal to A inverse H into AH, A inverse H into AH, and therefore H has the element inverse element A inverse of H, or the inverse of AH, inverse of the element AH is A inverse H, and vice versa. Okay, thus we have proved the existence of inverse. So we have now proved existence of identity, and then existence of inverse is also now proved. Now what remains now? We want to show that the operation obeys associativity. We want to prove associativity. Okay. Now to establish associativity, it is very clear that we have to take three elements. We need three elements. So those three elements are arbitrarily chosen three elements: AH, BH, and CH. Okay, you can see that here: AH, BH, and CH. And after that, after choosing these elements, you can operate the second and third element first. See, the preference or preference of operation is given to the second and third element, so BH into CH. After that, that result will be pre-multiplied by AH. Now in the bracket you can see that they combines, these two elements can combine and obtain BC of H. BCH, according to the rule, it combines and it gives us BCH, the answer, and that value will be pre-multiplied by AH, and finally you can see that they they can combine and obtain give us A into BC of H, or ABC of H. But after that, after bringing all the three elements of the graph of the group G together, and then you can add some preference. You can give some preference to the operations here. Then you can take a BC. Okay. Oh, that is the preference actually coming from this order, from this order. And now we want to remove that, or we want to open that preference, and we actually want to give a preference to A and B. So AB is given due to the associativity. Okay, due to the associativity of the operation defined on the group G, we can remove this bracket, and that can be fixed in the first position to include A and B. So A and B can be operated together first, and then C is operated to that. Then it is operated to H, and okay, that can now be written as ABFH. Okay, this is then ABH, then into CH, ABH into CH. But that ABH can be, but unfortunately that step is not there given. So you can then further it can be split on AH in dot BH. That bracket, in the bracket you can write that AH in dot BH, and after closing that bracket you can write CH, and associativity is also proved. So all these steps which we have discussed shows that the non-empty set together with that operation defined can make a group, that is G bar H acts as a group, and this group is called the factor group or the quotient group. Okay, that's all about that, the result on an important result on factor group. Actually, what we do here, we have shown that that factor group is actually a group. Okay, thank you.